Hello, I am Zhuo Shao. In this video, I want to introduce our research, one-shot transfer learning for population mapping, to you as a paper in CIKM 2021. In this research, we focus on the population mapping problem in one-shot transfer learning scenario. Population mapping problem aims to infer fine-grained population from coarse-grained population. For example, infer a population of 50 meter from 500 meters. The finer population is more valuable in a series of urban population, including urban planning, population schedule, transportation schedule, and commercial site selection. Um, in the real world, population distribution of fine granularity is hard to obtain because of the data collection heavily depends on the density of the established infrastructure, including closed-circuit television and base stations. This makes it especially difficult to obtain fine-grained population in less developed cities. Therefore, in this paper, we aim to infer fine-grained population distribution without enough fine-grained training data. Actually, there are several previous papers focusing on population mapping problem. However, almost all of them are deep learning-based methods, which are especially data-hungry and cannot perform well in our data-scarce scenario. Secondly, this method usually upscale the population distribution without considering the sequential information of population distribution. For example, when we are considering the population of 6 p.m., the population of its morning, 9 p.m., is also valuable for us to consider, but because both of them are citizens' commute time and they are correlated, the sequential effect is available to improve models' performance. In this research, we introduced four datasets of four Chinese cities, which length is 1 month, and we have the granularity of 500 meters, time granularity of 30 minutes, and for all scenarios, these four cities are always partitioned into two parts. In the source domain cities, we assume we can obtain sufficient coarse and fine-grained population distribution plus the POI distribution of any granularity. We know that POI is an important geographical static feature which could characterize the human activity in certain region, and it's a reliable proxy of human activity. In the target domain, we assume we could obtain sufficient coarse grain distribution and only one frame of fine grain distribution, which is we assume we could obtain one fine grain distribution via satellite nightlight photo or questionnaire, and it's quite easy to obtain. And we could also obtain a POI distribution of any granularity. Finally, we aimed to infer in sufficient fine-grained distribution in target city. To tackle this problem, we propose a systematical solution which is designated as PSRNet, which consists of three components. PSRNet stands for Population Super Resolution Net, and the first component called STNet, Spatial Temporal Net. It is designed for model-based knowledge transfer, and it's used as a backbone model for population mapping. It accepts a sequential coarse grain input and output only one fine grain population distribution, and whose time slots is the final time slots of the input sequence. And second component called PGNet, Population Generation Net. It is designed for database knowledge transfer, and it accepts the static POI distribution, and it's expected to output a fine-grained POI distribution, which plays the role of fake ground truth to supervise the domain adaptation in in target domain, and the third component called PADA stands for pixel level adversarial domain adaptation mechanism. It is designed as an optimization based knowledge transfer. It take the place of the regular fine tuning, and it would update the parameter of STNet, which is pre-trained in source domain, and let the pre-trained STNet adapt to the feature of target domain. And our specially designed PADA will mitigate the domain shift between source and target domain. Next, we are going to introduce the details of these three components. The first one is STNet. It's also consists of two components. The first one is SNet. It's a DenseNet-like population mapping model, which used to model the correlation between coarse and fine-grained distribution without considering the sequential information of input. And TNet is used to model the temporal data in the input sequence, and it would process this information and generate feature map, and feed this feature map into different layers of SNet to enhance the performance of the whole population mapping network. The second component called PGNet, and it's designed to generate population distribution, fine-grained population distribution with fine-grained POI distribution and specified time scala. In the first step, we will use several convolution layers to process the static POI distribution and map the time scala into a dense vector via embedding an LSTM layer. In the second step, we fuse the dense time vector and processed feature map of POI distribution into a time varying POI feature map, and process this feature map with several convolution layer to obtain estimated crowd-flow distribution. The crowd-flow distribution is defined as the difference of the of population distribution of consecutive time slots. Based on this definition, we could add the crowd-flow onto the reference fine-grained population. We have introduced. We in target domain we have one frame of fine-grained population distribution, and based on this distribution and our estimated crowd-flow, we could infer the population distribution of other time slots from forward direction and backward direction. However, we know that the error of our estimation will accumulate in this estimation process. The third component, PADA, is designed to adapt our pre-trained STNet into target domain, and in this component, we input the coarse-grained population from source or target domain into the whole system, and the first component is TNet, which plays the role of feature extractor, and it will extract the a feature map and feed this feature map into SNet and domain classifier. The SNet plays the role of predictor, which is updated to predict the fine-grained ground truth in the target domain, and the domain classifier is updated to distinguish whether the input population distribution is from source or target domain. And TNet have two updated update direction. The first direction is the same to SNet. It updated to infer fine-grained ground truths and help SNet for inference. In the second direction, it's updated to confuse the domain classification task and updated against the domain classifier. By this approach, we could adapt our pre-trained STNet into the target domain while mitigate the domain shift between source and target domain. Finally, here's the bird view of our whole system. And the whole process could be partitioned into two parts. In the first section, we pre-train STNet and PGNet in the source domain with sufficient coarse and fine-grained population distribution. And when it goes to the second stage, the domain adaptation stage, we first use the pre-trained PGNet to generate fine-grained population distribution in target domain to play the role of fake ground truths to support the PETA mechanism. And in the PETA mechanism, we use these ground truths to supervise for supervision and update the parameter of STNet and let the pre-trained STNet to adapt to the target domain. Our first evaluation section is numerical comparison between models, and in this section we introduce 8 baselines, which includes 2 classic models, 2 population mapping models, and 4 single image super resolution and video super resolution method. Except these 2 classic methods, all remaining methods are deep learning based models, and we built 4 scenarios, and we may transfer knowledge from city 1 to city 2 or city 3, and we also have different upscale factor, includes times 2 and times 4. Times 2 means we infer population distribution of 500 meters from 1 kilometer, and times 4 means infer a population distribution of 500 meters from 2 kilometers. And obviously, the times 4 a scenario is a harder task, and because we only have less valuable input. According to this table, we find that our PSRNet could always reach the best performance in all scenarios, and our PSRNet could reduce the error by at least 20%. We also noticed that it shows our PSRNet is especially effective in the with a higher upscale factor. That's all of these results shows the effectiveness of our PSRNet. In addition to numerical comparison, we also introduce a visualization comparison between our model and baselines. In this section, we compare our model and 2 baselines with the population map of ground truth, and we select a small region on the river bank, and we zoom this small map for 3 times. We find that the output map of our model have the closest texture and shape with the ground truths. When it goes to the urban FM, we could find that there's obvious vertical lines in the middle of the zoomed map, which is very unnatural. And when it goes to RBPN, we find that there is still predicted population in the river. Obviously, RBPN didn't capture the feature of the river, and that shows it both of these baselines cannot produce a reasonable output compared with our model. That also shows the advantage of our model. Finally, we have also considered an extreme data scarce scenario in which all data from other cities are not available. Concretely, only sufficient coarse grain distribution, one frame of fine grain distribution, and POI distribution in only one city are available. Facing this more difficult problem, we are inspired by this paper in computer vision field and developed an enhanced method based on original PSRNet. We pre-train STNet and PGNet on coarser grain population distribution and adapt pre-train STNet onto finer granularity. Concretely, we pre-train these two models to infer population of 1 kilometer from 2 kilometer, and in the target domain we train them to predict 500 meters from 1 kilometer. Surprisingly, we find that the error of our PSRNet is even lower than the cross-city transfer scenario, although our model only needs less data in this scenario, and that shows the domain shift between different granularities is lower than the cross-city transferring. Expanding these findings may become an important part of our future works. That's all of our introduction. Thank you for listening.